All right, so what we're going to look at today are sequences. After that, we're going to start looking at series, but I want you to just get used to what these lists of numbers are. So a sequence is just a list of numbers in a pattern. And a series would be if you took that list and added it up. So it's slightly different. One is a list and one is if you were to add up the list. The last time you did this was actually in Algebra 2, which how many years ago would that have been for you guys? So Algebra 2, then pre-calc, calc AB, and then calc B, so 2 or 3 years. So anyway, you do a little bit with sequences and series in Algebra 2. That would have been the last place you saw these. However, we're going to do some limits with these limits as we look out forever. So real quick at the top of the paper, just up by your name, let's review limits to infinity. Let me just make up a couple of examples. You guys can shout out some numbers to me and we'll like make these up. Let's do limit as n goes to infinity. Let's do, give me some numbers. All right, we'll do 5n plus 12 over 3n minus 7. Whenever the powers are the same, like these are both just n, what do we use? Coefficients. So this would just be 5/3. I'm just reviewing limits real quick, limits to infinity, because there's 3 ways this can turn out. They're either the same and you just use the coefficients. Let's do limit as n goes to infinity. Give me some more numbers. We'll do 40 over, I already wrote a 20. 27n plus 8. Is there an n in the numerator at all? No, that's n to the nothing. This is n to the first. So what does that equal? 0. Whenever the denominator grows faster than the numerator, it's going to go to 0. This is probably the one you need to pay the most attention to because it happens a lot. If the denominator grows larger than the numerator, it's going to go to 0. And then the last way this can turn out, let's do limit as n goes to infinity. Let's do n squared over n plus 2. So the numerator squared, the denominator's just n to the first. Do you remember what's going to happen with that one? So the numerator is bigger than the denominator. Yeah, it's like a slant asymptote. So it's going to go to infinity. It would either be positive infinity or negative infinity. We're going to positive infinity. So it's just going to keep getting larger and larger and larger. Let me recap again. If the denominator grows faster, it's going to go to 0. If the numerator grows faster, it's going to go to infinity. And if it's a tie, you use the coefficients. Those are the 3 versions of how that can turn out. Is this coming back to us? This was from Unit 1, so it's back in September. Okay. So number 1, write out the terms of the sequence. We're obviously not going to write out to infinity. Let's do like the first 8, okay? To get the first term, you're just going to plug in 1. You all ready? 1 squared. 1. 2 to the first would be 2. Minus 1 would be 1. 1 over 1, 1. All right, now let's plug in 2. 2 squared, 4. In the denominator, you'd have 2 squared minus 1 would be 3. Now let's plug in 3. 3 squared, 9. 2 to the third would be 8 minus 1, 7. Keep on going. What's the next numerator going to be? Actually, let's just do all the numerators first, because sometimes it's easier to do the numerators and then all the denominators. What's the next one going to be? So 16, let's just do all the numerators. I think that'll be easier. What'll be next? 25, 36, 49, 64. It's going to go on and on forever and ever. Okay. And then the denominators. So 2 to the 4th would be 16 minus 1, 15. 2 to the 5th would be 32 minus 1, 31. I don't have them memorized after that. I have to just think about it. 2 to the 6th would be 64 minus 1, 63. After 64 would be 128 minus 1 would be 127. And then, gosh, what would the next one be? 256 minus 1 would be 255. Do we see what's happening as we head out towards infinity? Like, are you seeing the pattern? That was my goal with doing that. I wasn't trying to waste your time. It's pattern finding. There's a pattern in the denominator too. It's 2 to that power and then minus 1. That's what, yeah, I mean, that's, yeah, like, yeah, no, I'm sorry. There wasn't any smoke and mirrors there. That's just what it is, okay? All right, limit as n goes to an infinity of this, and a sub n is what that formula is the limit of a sequence. So that tells you where the terms are headed. If that limit exists, the series converges to that number. If that limit does not exist, then the sequence diverges. Okay, so let's go ahead and try a couple of these. So for this one, limit as n goes to infinity of 2n plus 1 over n. This is why I just reviewed this for you. What is that limit going to go to? 2. Do you see how they're both n? It's n in the numerator and n in the denominator. So you use the coefficients. 2 over 1 would be 2. Now let's list out a little bit of the pattern so that you can see them heading towards 2. To get the first term, you're going to plug in 1. Ready? 2 times 1 is 2. Plus 1 would be 3 over 1 would be 3. If you plug in 2 for n, what would your second term be? 5 halves? Good. I love when I get 5 2s. 5 halves, 5 over 2. Okay. If you plug in 3, that's going to be 7 thirds, 7 over 3. If you plug in 4, that would be 9 fourths. Let's just do one more. 5 would give you 11 fifths. You keep on going. Do you see how those numbers are getting closer and closer to 2? Like 11 divided by 5, that's like really close to 2, because 10 over 5 would be 2. If you keep going, they're going to go to 2. Will it ever actually equal 2? No, it's like an asymptote. It's a limit. Okay. So let's try this one. Now, if you were to do limit as n goes to infinity of this 3 plus negative 1 to the nth, you're probably like, what on earth is going on? When that happens, my suggestion is write out a little bit of the pattern. Let's try plugging in 1. Negative 1 to the first. That'd just be negative 1, right? And then 3 minus 1 would be 2. Now, if you plug in 2, negative 1 squared would be positive 1 plus 3 would give you 4. Now, if you plug in 3, what are you going to get? 1, and then plus 3 would be 2, and then 4, 2. Do you see what's happening here? Okay, is that headed anywhere? No, so this diverges. There is no place where it is like headed. All right, number 4, limit as n goes to infinity of this thing, n squared over 2 to the n minus 1. So you have to figure out if the numerator is growing faster or if the denominator is growing faster. The numerator is polynomial. Technically it's quadratic, but polynomial. Anytime you have n squared or n to the third or n to the fourth or n to the fifth, that's polynomial. What is this called? Exponential. Exponential is going to grow faster than polynomial. So since the denominator is growing faster, this is going to go to what? 0. It's going to level off at 0. And let's list out a couple of the, oh wait, isn't that the one we already did? We did. Look, do you see how these are getting smaller and smaller and smaller? It's going to eventually go to 0. You're like, please don't make us list any more of those out, Ms. Cole. All right, now this one I don't have a formula for, so we're going to have to make one. All right, limit as n goes to infinity of what? Now I think it's easier to do the numerator and denominator separately. That's like my suggestion. And I'm going to let you guys struggle through this a little bit and you can talk to each other. Look at the numerator, and this would really be 2 over 1. Let's just do the numerator, all right? 2, 4, 8, 16. Can you come up with like a formula that we could write? You're multiplying by 2, but there has to be an n in there, like n is your variable. 2, not 2 times n, but 2 to the nth power, good. because this is 2 to the first and 2 to the second and 2 to the third and 2 to the fourth. So as n goes 1, 2, 3, 4, you would generate that pattern. No, because look at the third one. If you do 2 times 3, you would get 6, not 8. And if you plug in 4, 2 times 4 would be 8, not 16. No, you have to be able to plug in anything for n. All right, look at the denominator, 1, 3, 5, 7, the next one will be 9, and then 11. We have to write a formula that will give us those numbers if we plug in 1, 2, 3, 4. Perfect. If you plug in 1, you're going to get 1. If you plug in 2, you're going to get 3. If you plug in 3, you're going to get 5. Are you guys seeing that? Okay. So limit as n goes to infinity. The numerator is exponential. The denominator is linear. So the numerator is going to grow faster. So where is this headed? Infinity, which means it diverges. It's not leveling off anywhere. It's not headed towards any number in particular. It's just going to keep getting bigger and bigger and bigger and bigger and bigger. Now, whether you remember or not, you did also talk about factorials in Algebra 2. And these are kind of cool because it's with the exclamation point. It looks like n. You guys remember those sort of? Nope. Like I said, it's been a few years. So this would be n times n minus 1 times n minus 2 times n minus 3, so on and so forth, until you get all the way down to 1. So for example, 7 factorial, which looks like 7. It would be 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm seeing your head nodding. Do you remember that like vaguely? You did it in Algebra 2, whether you remember or not, it happens in there. It's like towards the end of the year. Like you keep going until you get down to 1. So like, for example, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. You keep going until you get to 1. Now here's my recommendation, and you can take it or leave it, but I'm going to make you write them out here. Memorize the first few, because it's good to just know them. You don't have to think about it. Now also 0 factorial is 1. Kind of the same idea. You know how anything to the 0 power is 1? Like that pattern. Anyway, 0 factorial is 1. 1 factorial would be 1, just 1. 2 factorial would be 2 times 1, so 2. 3 factorial, that would be 3 times 2 times 1, which would be 6. 4 factorial would be 24. And 5 factorial would be 120. Those are the ones I have memorized. You can memorize further if you want. You can choose to not memorize any of them and just have to think through it every time, but that's my suggestion. I just think that it wouldn't be a bad idea if you just do those ones. Does this make sense? Okay. So looking at this, we would do limit as n goes to infinity, 1 over n factorial. Well, the denominator would be growing astronomically large. So where is this headed? 0. And let's list out the first few of them just to see the pattern, because we just like went over these. You would have 1, and then you'd have 1/2, and then 1/6, and then 1/24, and then 1 over 120. Do you see how it's getting closer and closer to nothing? Is the idea there? And then let's do the same thing for this one. Limit as n goes to infinity of 2 to the n over n factorial. So the numerator is exponential and the denominator is a factorial. Up until this moment, exponential has always been the most powerful function you guys have dealt with. Like exponential beats everything. Do you know what I'm talking about? Like you're like, oh, well, exponential is going to grow faster than anything. Not a factorial. A factorial is going to grow faster than an exponential. So since the denominator is growing faster, again, this one is going to go to 0. Let's just write a note. A factorial grows faster than exponential eventually. And I'm going to show you what I mean by that eventually, because it actually doesn't grow faster to start out. But if you're going out to infinity, it's eventually going to take over. Yeah, and I think it's kind of cool. I don't know, it geeks me out. So since I'm the teacher, and I'm in charge, you have to go along with what I say. But anyway, let's look at the 2 to the n. If you plug in, well, actually, let's not do plugging in. 2 to the n, you're just going to keep multiplying by 2. It would be 2 times 2 times 2 times 2 times 2 times 2 forever and ever and ever and ever and ever. Now, if you do n factorial, I know I usually start at the bigger number and work my way down, but say you didn't know how far it needed to go, it would be 1 times 2 times 3 times 4 times 5 times 6, and forever and ever and ever. If you didn't know what n was, you don't know how far you need to go. Now, when you compare the first few, the exponential is actually going to win. Like, look, 2 is bigger than 1. Let's see how long it takes for the factorial to take over. Say you do 2 terms. 2 times 2 would be 4. What would we have down here? 2. Okay, so exponential is still winning. 2 times 2 times 2, this would be 8. This one would be 6. Okay, exponential still winning. But when you get to 4, what would this be? 16. And this would be 24. And then it's going to keep on being larger thereafter. Now, I did this with 2 to the n. If you did 3 to the n, it would take a little longer for the factorial to catch up. Thank you for heads nodding. All right. And if you had like 5 to the n, it would take a little bit longer. But no matter what, if you're going to infinity, the factorial is eventually going to take over and grow faster. And you guys really look like completely glazed over today. Is everything okay? Okay. All right, well, here, we'll do one more and then I'll give you a break, because that's after this one, that'll be a good place to start. All right, if the limit as n goes to infinity of the absolute value of the sequence is 0, then the limit as n goes to infinity of not the absolute value is also going to go to 0. Essentially what that means is you can ignore the fact that it's positive or negative, because look at this one that I made. And I don't know why the second term ended up bold there. I don't know why that happened. But anyway, do you see how it's alternating? Negative, positive, negative, positive. What this is saying is you can ignore that negative, positive. Now this one, again, I'm going to kind of throw you in the deep end here. I'll get you started, but you have to write a formula for this. And I think it's best if you do the numerator separate from the denominator. Here's how you handle the alternating part. If you put a -1 to the n in there, that's going to make it alternate, because anytime you plug in an odd number, you'll get a negative. Anytime you plug in an even number, you'll get a positive. Does this make sense? Hey, but Ms. Cole, what if you wanted the first one to be positive and the second one to be negative? Then you would just do this. Okay, now we don't want to in this case, but it's really easy to fix that. Now, I want you guys to think about it and talk to each other. All right, it is 3 to the n minus 1. You would take 3 to that power and then subtract 1. All right, now let's do the denominator. 1, 2, 6, 24, 120. Your hint for this one is we just talked about this pattern on the other side of the paper. 1, 2, 6, factorial. Perfect. N factorial. That's another big reason I say just memorize those first few, because when that shows up, which it does a lot, you'll just recognize it. Okay. So let's do limit as n goes to infinity of the absolute value of this. Now, when you do the absolute value of this, it means you just leave off this part. The absolute value would just take off that -1 to the n. You're just ignoring the fact that it's alternating. And because the factorial grows so quickly, where is this headed? 0. The denominator is growing super fast, so it's going to go to 0. So that goes to 0. And therefore, limit as n goes to infinity of the whole thing also goes to 0. All right, so we're just going to go over a couple of vocabulary words here and then just look at a few more examples. So monotonic means that all your terms are always, oops, I can't write, terms are always increasing or always decreasing. So they're only headed in one direction is what that, and mono means one. So, monotonic, just your terms are always increasing or always decreasing. They're just headed in one direction, which a lot of them are. Bounded means all of your terms stay between two values. Bye, have a good one. So all your terms stay in between two values. They're bounded. I mean, that makes sense. Like that's what bounded means. So unbounded sequences are divergent. So if it's not bounded, then it's going to diverge because it's not stuck anywhere. It's not going to like head towards any number. It keeps going and going. Then it's going to diverge. So we're going to state whether these are monotonic or not, whether they're bounded or not, and then whether they converge or diverge. All right. So number 9, or I just read all of the instructions. So we're going to state those 3 things. All right. So for this one, and a bunch of these I pulled just from the other side of the paper. If you start writing out the list of terms, this is going to be 2, 4, 2, 4, 2, 4, so on and so forth. So would you say that that's monotonic or not monotonic? It's not monotonic because it goes up, down, up, down, up, down. So monotonic just means all the terms are always going up or always going down. And so since those aren't, it's not monotonic. Is it bounded? Are we stuck in between two values? Yes, we're stuck in between 2 and 4. So it is bounded. Or I'm sorry, not n, a sub n. Plug in whatever you want for n. And then does it converge or diverge? Is it headed anywhere in particular? No, so it diverges. There's not like that asymptotic behavior, like it's not leveling off somewhere. It's just going to go 2, 4, 2, 4, 2, 4 forever. All right, so let's list out a few of the terms for this one. So if you plug in 1, you're going to get 1. If you plug in 2, you're going to get 4/3. If you plug in 3, you're going to get, what would that be, 6/4. If you plug in 4, you'll have 8/5. 5, you're going to have 10/6. That's probably good. You can always do more if you need to. All right, so are those terms monotonic? Are they always going up? They're not going down, obviously. So they are always going up. Yes, so this is monotonic. The values are always increasing. And is it bounded? Well, let's see. Let's do our limit as n goes to infinity for this. If we were to take this list out forever, like I only did the first 5 terms and then wrote ... but if you kept going forever, it's going to go to 2. Will it ever actually reach 2? No, that's just where it's headed. So all of your terms are stuck in between 1 and 2. So it is bounded. 1 was our smallest number, and then they keep getting bigger and bigger and bigger, and then they're going to get closer and closer to 2. So we're stuck in between 1 and 2, and so it converges to 2. And then for number 11, writing out the first few of these. This is the same one. I think that's the very first one we did, wasn't it? N squared over 2 to the n minus 1. So if you plug in 1, you're just going to get 1. If you plug in 2, that'll be 4/3. And then what was the next one? Plug in 3, 9/7. And then 16/15. And then, here I'm trying to do my 25, 30 firsts. That's good enough. You have them all on the other side of the paper. Or not all of them, but we did a bunch of, obviously you're not going to sit there and write out the list forever to infinity. You'd never be done. All right, so is it monotonic? This one's not. 4/3 is bigger than 1. So this goes up, but then what starts happening after that? Starts decreasing. Okay, so it goes up and then it starts to go down. So this is not monotonic. It just goes up very, very slightly and then starts to go down. If you think of like a graph, I don't know, because I like a visual, it would be something that like went like that. What's that? Oh, from stats? Don't talk to me about that. Okay, so if you do limit as n goes to infinity of this, where did we say it was going? I know we wrote it on the other side of the paper, but write it again. It's not going to hurt you. 0. And so is it bounded? Yes, we're going to be in between 0 and how big does it get? What was the biggest number? 4/3. Good. So it is bounded in between 0 and 4/3. And it converges to 0. If you get an answer with that limit, like that doesn't go to infinity, or it's not something silly like 2, 4, 2, 4, 2, 4, then it's going to converge. This one converged to 2, this one converges to 0. And then last one, let's start writing out a little bit of the list. If you plug in 1, what are you going to get? 2. And then if you plug in 2, 4, and then 8, and then 16, and then 32, and so on and so forth. So is that monotonic? Yes. Keeps getting bigger. Never gets smaller. Is it bounded? No. And does it converge? No, because what's happening to these numbers? Yeah, they're just going to keep on getting larger and larger and larger. So it diverges.